Okay, hi everyone, I'm Leonardo Lamanna. I'm a postdoctoral researcher at the Fondazione Bruno Kressler in Italy, and this is a work about still learning action models in partially observable environments, which is a joint work with Alfonso and Alessandro from the University of Brescia. So I think I can skip the motivation because, I mean, this is the third paper, so, you know, learning domains is, specifying domains is time-consuming or prone, is not always feasible. So the objective of this work is learning a model of the environment dynamics, which is expressed as a set of, translates to learning the preconditions and effects of the planning operators. And we don't do this without any assumption. So we are in an offline learning setting. That means you assume to be given a set of input traces, which consists of states and action sequences. And we do not assume that the traces are fully observable, so we can have that there are some missing literals in some state of the trace, or also some missing action between two states. And we assume the predicate and operator signatures to be given. So we know what are the input parameters of the actions, the input parameter types, the predicate types, and so on. So what's the input and the output of the algorithm that we propose to learn these action models in partially observable environment? We have the set of predicates and object types, and here, for the sake of presentation, there is just one trace, but you can imagine we may have a set of traces here. So the output of the algorithm is a set of action schemas where we just fill the preconditions and the effects of each action, which are lifted, so operators, and this is done by applying some logical rules. So the overall idea of the algorithm is iteratively applying these logical rules till the model has been refined and the observations in the traces, like the states and the actions which are not observed, have been possibly completed. So they've been possibly added to the traces. And we have three main types of rules, which are the rule for learning preconditions and effects, propagating known effects, and reasoning about possible effects of the actions. And we are going to see each of these in detail. But before this, let's talk about how the algorithm initialized the model. So we have that at the beginning, since we know the action signature and we know the predicates, we can generate the set of all possible effects or all possible preconditions, meaning all possible predicates affected by an action. So this is what we do, and this is how we initialize the set of preconditions. So at the beginning, we have all possible preconditions and no effects. But we keep track of an additional data structure, which are the set of potential effects of each action, because we say at the beginning, since we don't know anything about the action, any effect may be true for the domain. So we keep track of this set of potential effects, both additive and delete effects. So the first set of logical rules that we apply is quite straightforward. We just, so here we have this example of a trace, which is going to be our running example. So we just remove the unsatisfied preconditions. So since we assume that without a lot of generality, by the way, here we are considering only positive preconditions, and we assume that they are all preconditions at the beginning. Whenever something is not satisfied, we can just remove it from the set of preconditions for that operator. And we can do another straightforward rule for the effects, which is like whenever something was false and became true after executing an action, it is an additive effect, and vice versa, it is a negative effect. And these essentially are the rules typically applied in fully observable settings. But one additional thing that we can do is removing from the set of potential effects the ones that are logically inconsistent with the trace. So for example, here we have that there is a potential effect of the action pick A, which is false after executing the action. We don't observe it before executing the action, but only after. So we cannot say it's a negative effect, but we can say that it is definitely not a positive effect, because otherwise that would be logically inconsistent with what we observe in the trace. So the second set of rules is about filling the states in the traces, so filling the missing literals in the traces. And we can do this by, for example, adding what we learned to be an effect. So since before we learned that holding A is an effect, or I would better say holding X is an effect of the action pick X, then we can, for example, in this last state, add the literal holding C, because we are executing pick C, and we know it to be an additive effect. And this is a simple example, but you can imagine if you chain multiple states and you have different actions, then this may allow you to learn something more about another action. Similarly, and this is also why we keep track of the potential effects, we have that we can propagate between different states, subsequent states, what is not affected by an action. So in the previous example, we saw that we could remove this on AA from the set of potential additive effect of the action pick A. So here we are executing pick C, and we can propagate this not on CC to the next state, because it's definitely not made true by the action. So this is another way to fill the states, which again can allow to learn something more about other actions in the future or in the past, because this can be done also in the opposite backward. So the third set of rules is about learning something that is not directly observable in the traces, which I think is maybe also more interesting. So consider this example where we have that there is a predicate on table A that becomes false after executing two actions. So we can say either pick A or stake AB made it false, but we cannot say which one. But we have three possibilities. Either it is a negative effect of pick X, or of stack, or of both actions. So the idea is that we want to consider all these possibilities. And to do this, we make use of additional predicates. So essentially, we split the predicate, like the observed effect. We split it into, in this example, two predicates, because we have two possible actions, where we say, OK, on table 1 is the situation where pick of A make it true, while on table 2 is the situation where stack AB makes it true. And these can also be seen as having different models, where in a first model, M1 on table X is a positive effect of the action pick. In the second model is a negative effect of the action stack. And in the third model is a negative effect of both actions, because that's also consistent with what we observe. So now that we have all these models, we need a way to select or filter them out. So how do we choose between these models? One thing we do in the paper is defining a partial order relation between them. I don't want to go into the technical details, just give the intuition that a model is smaller than another model if it has more precondition and less effects. So you can see also that this is not this is a partial relation, because you might have that you cannot say that a model is smaller than another model because you have multiple operators, so it may be smaller with respect just to a single of them, to a single operator. And then once we have this order relation, we define the concept of minimal model for a set of traces, which is a model consistent with the traces, such that there is no other model consistent with the traces that is smaller than that model. So essentially, the minimal model is a model that has more preconditions and less effects than other models consistent with the traces, and is comparable with these other models. So here you can see an example, which still is our previous example, where we have that M1 is less than M3 because we have, so here is not visible, but the pick action here is the same. So the stack action here has more effects, and we say that we need less effects if we want a smaller model. So M1 is smaller than M3, assuming that the preconditions are equal, which are omitted for the sake of presentation, but here we are assuming that they are, for example, all possible preconditions. And similarly, M2 is smaller than M3, but we cannot compare M1 and M2, for example, because we have that M2 is smaller than M1 for the pick action, because there are no effects here. but the opposite holds for the stack action. So they are not comparable with each other. Okay, so once we have all these minimal models, we can aggregate them in some way. And we do this by defining this notion of cautious model, which is the model obtained by making the union of the preconditions of all minimal models and by intersecting their effects. So the intuition is that an action is applicable in this model. If an action is applicable in this model, then it is applicable in all minimal models. And if something is an effect in this model, then it must be an effect in all minimal models, which are indeed consistent with the traces. And we have this warning that, okay, this is not guaranteed. I mean, if we compute a plan then with this cautious model, then we are not guaranteed the plan to be executable in the environment. So here is an example of a cautious model obtained from these two models where we just compute consider all possible preconditions and the intersection of the effects. So our algorithm applies these logical rules to compute the minimal models, as we saw before. And in the paper, we prove these rules to be sound and complete with respect to the problem of computing all minimal models. So the computed models, by applying these rules, are minimal, and we don't miss any of them. So as output, we can have, at this point, that the algorithm produces all minimal models, and then it derives the cautious model. And this is the output of the algorithm. Then we have additional theoretical properties in the paper. So we experimented with this on a set of benchmark domains from previous IPCs. And for each domain, we generated 10 plan traces of length 10. So each plan trace has 10 actions, and these are some statistics about the problems that were used for generating the traces. And since we are in a partially observable setting, we just remove from each state of the trace a literal according to some uniform probability ranging within this range. And we evaluated the learned models by means of syntactic assimilarity, where we just compare the preconditions and the effects of the models. So, for example, we have that if a precondition is in both models, is a true positive. If it's just in the learned model, is a false positive. If it's missing in the learned model, is a false negative. So we can derive then precision and recall on these true, false positives. But we also compute the ratios of valid planes and lost planes that we are going to see in a while. So we perform an in-depth analysis of our algorithm in the paper. Here I'm just showing the comparison with FAMA from Diego. So here we have the syntactic similarity, and we see how it evolves when the observability is increased. And you can see that in most of the situation, this method can outperform the current state of the art on in this setting. But still, there are some cases where FAMA is competitive, which is when we drastically reduce the observability. So when we really observe nothing or more than nothing, something more, we don't learn something good, anything. Okay, but what about then using these models for solving the problems? Okay, that we can learn something that is syntactically similar, but then is it useful in practice? So we also evaluated the ratio of valid planes computed by means of these models on a set of test problems for each domain. And here you can see that the models computed by this approach are very effective for solving the problems, because the planes are almost always valid. Even when you have a very low degree of observability, you have a very high ratio of valid planes, which doesn't mean you are solving all problems. That's the small number here. So out of 1,300, we are just solving 300 problems. But out of these 300 planes, almost all are valid. And we also compare, evaluate the lost places, which are the places that are computed by a ground truth model or a reference model, but cannot be computed by the learned model. So this, for example, if you solve a problem with the ground truth model and you obtain a plan, then this plan is not executable in your learned model because of some additional preconditions, then you are losing that plan. So this is the idea of this table. And from here, we can observe that this approach is less permissive than FAMA. Okay, so we integrated already this algorithm into an evaluation framework called the MLGym. So you can really play with it if you would like to. And here is the link to the documentation. There are some tutorials, so we are trying to make it even more accessible and usable. So that's the end of the presentation.
Questions? Enrico.
So, thanks for the talk. So I was wondering whether you can relate somehow the cautious or the minimal models with the ground truth models, somehow, or they are like, so are they like, I don't know, under approximation, over approximation?
Okay. It depends, because for the preconditions, they are over-approximating. For the effects, they are under-approximating the ground truth models. So the intuition is that you remove from this initial set of preconditions the minimal set of preconditions, which is equivalent to maximizing the set of actual preconditions in your learned model, while you also add the minimal set of effects. So this may be some relation with the ground truth, is that in that you are trying to minimize what you're not daring anything, like no guesses.
Okay, thank you. Jonas, then Patrick.
I wanted to ask again, what is exactly the input that is not completely observable? So which kind of input is actually given?
Okay, so the input is, I have some slide somewhere, is a domain, an empty domain. With that I mean a domain where you have the predicates, the object types, and the action signatures. So this is the input domain, where you just remove all preconditions and effects. And you have also a set of traces. And you can have missing information in both the states, but also you can have missing actions, if that was your
A complete action, or are you missing an action partially? So is it just an edge that tells you there was something, or is maybe a stack, I know it was the first block was me, but I do not know the second block?
Well, here we consider the case where you do not know anything about the action, but it can also deal with some, for example, missing parameters, because I had no time to dig into these, how we deal with partial actions here. But the idea is that whenever you don't have an action, you compute the set of all possible actions that could be executed there, and you try to infer something that is common to these all possible actions. So if you have a missing object, just a missing object, you have a set of possible actions, which is, let's say, smaller than the set that you have if you have no information at all about the action. So the idea is that you compute the set of possible actions and you see if there is something that you can infer, like, okay, whatever action I execute, I make this true. So I can add this literal to the next state, for example.
Okay, sounds similar to our approach. We did not add a constraint if we did not know an object in a certain case, or an action. So we basically just decode the action in certain cases where we needed that object.
Okay, so you take it offline, so let's move again to the next one. Yeah.
So, well, a special case of partial observability is no observability. Right? So in the, let's say, the two possible cases, one where you have complete observation of the action, but no observation of state, nothing at all. and the other case you have complete observation states and no observation actions. What can you sort of roughly say what would happen if you apply this method to either of those two cases?
Okay.
Somehow, but do you have any intuition on what the result will be?
Yeah, that sounds a very difficult problem. That's also why it was really interesting, the previous paper. Yeah.
I can simplify, so Patrick. So let's say the 15 puzzle. Okay, so I give you a state, and I just give you the name of the action, up, down, right, and left, and I don't give you the arguments. Okay, so in some sense,
that's even more than
I know, that's why I'm making it simpler, because you're asking us to match. Okay, so the 15 puzzles, so you have these 4 labels for the actions, okay, and you don't have the action arguments, but yeah, I give you the state. Mm-hmm.
So the idea of this approach is that it tries to infer what is, even if it is not observable, is common to all the models consistent with the trace that you give as input. If you, for example, have no information at all about the action, then I'm not sure you can infer something about something that is common to all possible actions. So you may guess something using some appropriate criterion, but this is not the case for this approach.
Imply a disjunction of some sort between these two states. Some action happened and it has some effect.
Actually, I think that there's a paper by the Prague group, okay, that say that that's not polynomial. So, in a sense, learning without any information about the action argument, not even the arity, give it a full state, it's still in the general case, it's not polynomial. Okay, so, time for one last question. Yes?
Great work. I just had one clarification question about input. So if I don't have state observable at all for intermediate actions, do I at least know that n number of actions were applied? Because for the case with no observability, I can have cases where I cannot see the state at all. I might not even know that some action is applied, but at least can I know that n actions were applied to go from this state to another state?
In this case, yes, you know that there is some sequence of states where you do not observe anything, and maybe sequence of actions, which are the transitions for these states. What you are talking about makes me think about macro actions. So I think you could kind of manage these and aggregate all with a macro action and learn some micro action model, but definitely this is not part of this work.
Okay, so thanks a lot. Grazie, Leonardo.